And let's see a lot of different aspects of this mixture of prime numbers and differential equations. Okay, so differential equation modulo of powers of primes. Okay, so I mean, I will try to just say this simple observation that last year I made, and I didn't find literature really this kind of very simple things, which seems to be a mathematics of Eisenstein 200 years ago. But anyway, let me try to write down what is this simple observation. So again, I will start. Today I will talk about two classes of differential equation. One will be about linear differential equation, the other one vector fields. And I will not prove something. So the class of differential equation that we are looking at, these are called linear differential equation. So Z will be in C. And if you want, these are vectors, Y M, let's say Y N, Y I's, let's say they are holomorphic functions on some open subset of C. And so we are dealing with this kind of differential equation. And these are AZ. A is just AIG is a matrix, n times n. So this is n times n. And AIGs is it rational functions in Z with coefficients in C. Whatever I'll tell you. Maybe it is simpler that you just forget the coefficient over C. Take coefficients over Z. I think it will. But the whole discussion can be done for when the differential equation is defined in some sense over integers. What we are interested on this differential equation. So the question is, when all the solutions y of this guy are algebraic, and what is this means that its entries there are, for example, if any solution that you take, there will be polynomials a priori with coefficient in complex numbers, polynomials such that pi z yi at the holomorphic function is 0. For example, e to the z is not algebraic, whereas square root of z is algebraic, and so on.
Hossein, may I ask a question?
Yeah, tell me, Sergey.
So why do you need to restrict your equation on the domain U? You study rational functions, so you may assume that it's actually the whole of C or even the Riemann sphere.
Yeah, I will not do analytic continuation and so on. So that's why I say that there are some solutions, some open subset. But I will not talk about the analytic continuation around the singularity. So these are, there will be, as a function on C, they are multi-valued. But for them, I will not touch this monodromy issues and so on.
Okay, so your study is purely algebraic.
Yeah, I will just play algebraic things with this rational functions. That's the reason. Yeah.
Okay, thank you.
Okay, so the main question is that when we have a differential equation, linear differential equation, or in general, the thing that I'm saying is valid for a big class of differential equation, not necessarily linear. We want to decide for when they are algebraic. For example, maybe in okay, maybe I will tell later. So the idea is that it is possible to play modulo p stuff with this function and to guess when this happens, I want to tell this one. So in this general context defined over C, I will, for example, I will use ring R, the Z module generated by coefficients of A, AZ. Maybe in order to better, maybe sometimes I write this one. I take the denominator of this guy outside, so I write it as divided by delta Z another polynomial, and then another matrix Bij, and then Bij are now polynomials in Z. And when I'm saying that the coefficients of Z, it means that the coefficients of this polynomial and the coefficients of this polynomial. And as I said, if you take Z, then this means that at the end my R will be Z itself. And really, this generality doesn't make too much difference from the special case of Z. But in general, it is good to work over finitely generated subrings of C. So this R is a finitely generated subring of C. So the observation that, let's say, last year I was making, and I was trying to see what is the literature and so on, is this one. If all the solutions of this are algebraic, then maybe I write this one. Then something happens, and what is this something? Then there is this n, some n in this ring, or maybe if you take there is some integer such that entries of, maybe I write and then n delta, I write and then a m n r in Rx, and then what is the am? These AMs are recurrently given by this one. A and A1. Okay, A1. So let's digest the thing. No, I take the complex, and then I define, and now after this definition, everything is defined over RZ now. Okay. So first of all, you take a matrix with rational coefficients, and you've defined it as recursion. So that this recursion AM plus 1 is derivation of AM with respect to Z, and the AM times M. These are n times n matrices. And in a minute, I will say from where this comes. So you will get, again, a matrix of rational function. It is huge. So you will see that this has a pole order, A itself has a pole order 1 at delta Z. When you do these things, this means that at the end, the AM has a pole order M at the delta. At the end, this delta M, AM, these are the entries, these entries of this are in RZ. This is so these are all polynomials. So
the matrix AM is the matrix of the system which is obtained by mth.
Exactly. I will write this one. I will write this one in a moment. So maybe I write it. So the AM is described in fact that this m's derivative of y is AM y. Okay. So this is the m's derivative. But anyway, this is AM. We compute in this way. The point is that there will be some n such that when you multiply AM with n to the m and delta for killing the denominator, this has still coefficients in R, okay? And remember that R is a finitely generated subring of C. But the point is that I am dividing over m factorial. Dividing over m factorial, this means that I am dividing over all possible primes when m increases. And the main content of this proposition or theorem is that apart from some primes, which has to do with this n, all the other primes in m factorial must be eliminated with whatever something in the denominator, and at the end of the day, you don't get all the primes in the denominator. Once again, I am remembering that R is Z, some coefficients, and it's a finitely generated subring of C, and at most a finite number of primes might be invertible. And again, I remember that rational numbers is an infinitely generated subring of C. Rational numbers of Z, 1 over 2, 1 over 3, 1 over P, and so on. Rational numbers in infinitely generated subring of a complex number. This is a finitely generated. And the theorem says that something happens in this denominator is so special that the primes will be cancelled. And only a finite number of primes might survive in the denominator. And so, I know I will reach. At that time, I was trying to understand this Grothendieck-Katz conjecture and so on. So it is a natural to make this conjecture. So what it means that if you have a differential equation and you see that there exists some n such that this combination, the primes, almost all the primes cancelled in the denominator, and at the end you land on again finitely generated ring, then the differential equation must have only algebraic solution. But the situation in the literature is that this has not been formulated in this way. Otherwise, there is this Grothendieck-Katz conjecture that I want to mention. This one. Okay, so fix a prime, and so in the literature, let me see where I have written. Okay. So this hypothesis.
Hossein, how difficult is to prove this theorem 1?
No, it is very easy. I think it is Eisenstein, actually. In the first, I am talking about the text of my leafy scheme and Hodge-Loci. And actually, it's just in the first chapter. It is just reformulating criterion Eisenstein. You can prove it easily. I can send you where the proof is in my text, but it isn't just the first page.
So it's essentially a straightforward computation.
Exactly. Algebraicity is a very strong condition. I mean, it gives the Taylor series of solutions of algebraic functions. They are very special, and that's and basically I could say I just reformulating the Eisenstein criteria, nothing more. But what I want to say that this is not known in this is not at least not written in the literature, and then I decided to write it, even so it seems very elementary. What is known in the literature is that when we fix a prime, we are interested in a piece. This means that we iterated your differential equation p times, and the issue is that consider this one as a matrix in R. Let's say Z. Well, when we have to. I didn't multiply with delta to the p. then maybe let I invert the delta also. And then I want to take a modulo P of this matrix. This means that P in this. So what I'm basically doing is I want to take AP modulo P. And whatever it is written is there. This thing implies for almost for all prime numbers except the finite number. Except the finite number has to do with this finite number of prime which are invertible in my ring and so on, except the finite number. Then AP modulo P is 0. This means that AP is divisible by B. And at the end of the day, this Grothendieck-Katz conjecture Katz P curvature conjecture. What it says that if this happens, then the differential equation must have only algebraic solutions. So if let me say if this, so let me call this one 1. Maybe having algebraic solution, let me call it 0. If 0, 1, and then 2. If 2, then 0. So if the P curvature is 0 for almost all prime, then the differential equation must have algebraic solution. So maybe the diagram is this one. Then they have 0. 0 implies 1. 1 implies 2. And what I'm saying that the true conjecture must be this one. 1 implies 0. But what is formulated in the literature is this one, Grothendieck-Katz. And actually, after realizing this one, I tried a little bit to play if there are ways to find counterexamples to Grothendieck-Katz. I failed, but I think a lot of people believe that it's still, even so, this data is much less than, the data in 2 is much less than the data in 1. They still believe that this 1 implies the algebraicity. But maybe I say at least one example of computation I tried to do, and at least to justify the title of my talk. So the point is that we are just taking some partial data in this one and formulating Grothendieck-Katz. But there are a lot of other data that we are putting in the trash. So maybe just to a little bit explain this one. For example, if you take MPK, so let me say k integers equal to smallest m such that order of P of m factorial is bigger than or equal to k. For example, MP1 is P, MP1 is P. Exactly, the P factorial has already one P, and then MP2 equal to 2P, etc. So from one, for example, what here you can conclude that there are more congruency happening. This AMPK modulo PK equal to 0 for almost all prime. Again, one has to take out some finite number of prime. This star means that not for all prime. But what I am saying that even if you collect the powers of P in this m factorial, still you claim that P to the K divide this, the entries of this guy. So there are more congruencies going on. And at the end of the day, for me, it was a completely, let me call this one, for example, 3. So what I am saying, at the end of the day, this Grothendieck-Katz conjecture implies that 2 implies 3. This means that if you have modulo P, your AP is modulo P is 0 for all except y and prime, then there are a lot of things happening also modulo P to the K, which in some sense for me it is not reasonable. But anyway, the hypothesis is very strong. But at least I came to the conclusion it is better not to believe on the conjecture, like, and try to do some kind of computation, trying to analyze the P curvature, P to the 2 curvature, P to the K curvature, and so on. And I will just write down one example that I found. I think it is good to see the theory of this example. But it will not a counterexample to this one, but I think it is good to elaborate this example. So maybe I write this linear differential equation, Lamé equation. I took, well, Lamé equation depends on many parameters. And then I, at the end, after doing computation with a lot of examples of Lamé equation, I was able to find this one. And I want another one, but I think one has to really see what is the theory behind. I am not sure if there is any literature. Fix to the z2 dy dz minus 736 zy. Well, this is not written in the format of system, so it is a kind of differential equation. But if you want to write it as a system, then you have to define this. You define this vector. You make the derivation of this guy. So this will be, let's say, again, you write it in terms of this guy. So you make the derivation of y. This is 0, 1. And then the second derivation, you calculate from this differential equation. So this will be 4z3 minus 1, or z3 minus 1. For example, here in the first derivative, for example, here it will be plus 736 z, etc. Anyway, this is the linear differential equation. But this version is a kind of writing as a system, as a matrix that you can produce the P curvature thing. And let me say that what is the statement? This is highly done by putting the computer running, searching for example, proposition. A P5 curvature of this guy, modulo 5 is 0, but a 5 to the 5, and actually, even I was not able to find 5 to the 2 or 5 to the 3 examples, but I don't know why it happened that it's 5 to the 5. And if you look in this one, modulo 5 to the 6 is, here must be the power of prime. Here this MPK, but it turns out that the MPK also is a power of prime. I don't know if there is any meaning on this, and this is not 0. But anyway, this is, let's say, this is, so the 6 is a K, P is 5, and the MPK is 5 to the 5. Okay, so, but the point is that this is not a counterexample, of course. And what is the reason this is not a counterexample? Because the hypothesis of this. If the Grothendieck-Katz is true, then 2 implies 3. But the point is that this differential equation, if its solutions are algebraic, then we can say that it is a counterexample. But the point is that one can verify that the solutions of these differential equations are not all algebraic. It has transcendental solution. But anyway, at least independently of the world of differential equation with algebraic solution, P curvature doesn't imply MP curvature 0. And I think it is, well, there are a lot of, some literature, starting with the works of Yves André, many other people. But I think one has to really go through the literature, and especially I think the people who are not so interested in computation, I think this kind of mathematics, you have to really do a lot of computation to observe something. Okay, so this is the first part. And the theorem that I wrote really is elementary. I think if I give it, if whoever knows something about a formal power series is substituting in differential equations and so on, can prove it easily. And the basic content is just the whatever Eisenstein did 200 years ago, almost 200 years ago. So I will not focus on the proof. What I want to do, I want to introduce the vector field version of this kind of conjectures, and I think it is worth. Well, let me say the vector field version. So by the way, the vector fields are also differential equation. In algebraic geometry, we don't care about vector fields as differential equation. They are just sections of the tangent Baldun and nothing else. But the vector fields are the main ingredients of ordinary differential equations. And I will not do again ordinary differential equations here because, but let's say. So vector field. So in the remaining time, I will just introduce the vector field version of all these statements. So again, I can take some scheme and so on, and put in a purely algebraic framework. But I will not do this one. I will just consider vector field as a. So you have a ring R. Let's take again R, finitely generated subring. If you want to take as integers, indeterminate variable. So it's a derivation of this ring. This is, at some point I will put the letter X. And usually we write it as, for example, V1x, VDX1, VNX, VDXN. And as I said, any vector field is really, it is, you can consider as a differential equation. The way that you consider as ODE is that you just, if you want, you take this complex number to do complex analysis, where x1 dot, v1x, xn dot, vnx. And then you will have to do a course of ordinary differential equation to see that these things can be very complicated solutions. For example, there is a Lorentz attractor at, I think I said, who is doing a real dynamical system. Just in R3, there is some complicated behavior and so on. But what I want to do, the vector field version of this theorem, the theorem 2. And I mean, at some point I try to produce the holomorphic foliation or this strange thing that I call leafy scheme version and so on. But I think just a vector field version is enough for our purpose. So the point is that I will forget this guy as an ordinary differential equation, just as a derivation. And so, and looking at it as a derivation, I can iterate. No, what v to the, okay. So again, if all the solutions of it are algebraic. But let me say just briefly what this means. So maybe very fast. So maybe if you take n equal to 2, maybe to make it easier. So let's say if you want to take it R2 or in C2. So vector fields are just to each point they give a direction. And I think most of us, maybe we have played this GeoGebra, that it makes the trajectories of these vector fields, which will correspond to the solutions of this one. So the solutions are algebraic. It means that if you take a point, for example, P, P, not a singular point of V. So what it means, singular point, it is not the simultaneous zero of V1, V2, Vn. And well, what we learn in ordinary differential equation or in holomorphic foliation when you are working over C2, there will be unique curves in the phase space tangent to your vector field. And algebraicity means that at the end, all these curves, which are a priori transcendental curves, they must be part of algebraic curves, in my case in R2 or C2. So again, there is a natural notion of what are the solutions are algebraic. So this has a very nice consequence similar to this one here, and the consequence is this one. Then again, there exists some n. This capital N always control a kind of finite number of primes which do not enter into the game, such that V to the m. So again, you iterate this vector field. I mean, making so let me say, so V of polynomial, what it is just it's a V of, let's say, V of polynomial is just this one. No? And so you have a map from the ring to the cell. You iterate m times. Again, there is this m that at the end you have to multiply n to the m. Again, this guy, in principle, it is again a map from Rx to Rx. But the point that when the solutions are algebraic, even you can divide it over m factorial. And even so, you are dividing over m factorial, a lot of primes will be killed in the middle of iterating all things, and then you will get into the original ring. And as I said, if you want, you can take R equal to Z. This means that dividing over m factorial over all primes which do not affect the image of this guy.
So this is for all n.
This is for all m. I wrote it. This is for all. I didn't write for all. Here for all m n. And again, I think well, the situation is similar, and I think the correct conjecture would be this one. Again, the same thing. Again, the 0 implies 1. But this one implies now something just in the case of m equal to prime number. So just you put m equal to prime number. Let me see.
1 holds for prime number.
Huh?
You mean 1 holds just for prime number, then the vector field is algebraic?
And I think I have made just a money. No, actually, there are many other versions. Let me. Let me see. I have to remember. Uh, actually, this. Okay. No. Something that I think I have made. You can. There are two algebraicity going on. First of all, the curve itself is algebraic. Second one is that then they have this solution, no? Z. Let's say these derivations with respect to some parameters. Z. Let's say you have some map from C0 to C2 in this case, Z going to X1Z, X2Z. There are two. Either you say that the image of this map is algebraic, or you can say that this as a function of this X1 as a function of Z algebraic and X2 is a function of Z algebraic. And actually, I don't know why I did this one. I wrote this. Now I am making the version of the conjecture such that X1 and X2 are algebraic as a function of Z. But what I am saying, this.
Let's say here the VI's are algebraic. You mean?
No, these are rational functions. VI's. These are polynomial actually. VP mod P, but I have to say that when I'm saying it here, it is algebraic. It's algebraic as a function of Z. But anyway, I have to look. Okay, but I think it doesn't matter. It is possible to make Huygens a version of the conjecture for vector fields. Again, the folklore things conjecture that the people has noticed when something modulo P happens, then they have claimed the algebraicity. And actually, I have not written here, but there are depending on this notion algebraicity. There is this issue of VP is collinear with P. Actually, I wanted to say this one, but I have not written. I have not written the corresponding statement here.
You said that V is algebraic indeed if x1 and x2 are algebraic as a function of Z. Is that it?
Now, in this one, I'm using as a function of Z. But what I wanted to formulate, and that the image is algebraic, and then if the image is algebraic, then we will get this condition that the VP is collinear with V in the modulo P. But anyway, I think I will not try to correct this one, but at some point we can discuss it further. And then I try to a little bit make it, the whole story started, I wanted to study the modulo P properties of something called Hodge-Loci, and then I started a little bit to look at the Grothendieck cats and so on, and I think I will finish here. As I said, it is the details are written in this text that I wrote there, and I think the main thing that at some point I will try to focus. Maybe even in the context of linear differential equation, a little bit going to this P curvature stuff, and to see this higher congruences when they happens and so on. Okay, I think I'm done. If any question, let's.